This is podcast 2.2 for AP Chemistry, and today we're going to talk about 3 different types of chemical reactions, describing reactions and solutions. So we're going to do molecular formulas, net ionic equations, and things like that, and then a little bit about solution chemistry. So there are 3 types of chemical reactions. There's precipitation reactions, acid-base reactions, and oxidation-reduction reactions. These are sometimes referred to as redox reactions. And this may sound weird to you because you're used to us talking about single replacement, double replacement, combustion. But in reality, all the reactions that we've talked about and all reactions in chemistry can fit into one of these 3 categories. So this is what most practicing chemists use in the real world, and it's how we're going to classify our chemical reactions too. So if we look at precipitation reactions, that's the one we're going to focus on today. A precipitation reaction is like a double replacement reaction that we talked about last year. It's a double displacement or double replacement reaction in which a solid forms and separates from the solution. What you're going to see with your precipitation reactions is an example like this. And if you remember, we had a big table where you had to figure out what was aqueous, what was solid. That's what these are. So we have silver nitrate, and it's aqueous, reacting with aqueous sodium chloride to give us a silver chloride that's solid, and then sodium nitrate aqueous. So what we're looking for when we're talking about precipitation reactions is what is the precipitate, and the precipitate is the solid that forms. That means it's really important that you understand the solubility rules and you're able to predict what that solid would be just by looking at the 2 reactants that go in. Here's an example using potassium chromate and barium nitrate. If we take potassium chromate and it's aqueous and we put it with barium nitrate, which is also aqueous, we're going to end up with a solid. We're going to end up with barium chromate. And then your other product, since that was barium chromate, your other product is going to be the potassium nitrate. And then we would need a 2 here to balance. What you're seeing right here, though, is called the net ionic equation. All we've done is we've just taken these spectator ions out, and we'll talk about those in a second. And we're focusing only on the 2 ions that come together to give us the solid, because the solid is really the important part. Everybody else stays the same. And if you look down at this, you can see pictures of what happens on the molecular level. So they're giving us a key of what everything is right here. You can see initially, before things start mixing, we have ions of everything. And then once they come together, the barium and the chromates come together and they kind of fall out of solution. They precipitate out of solution. And if you did this in real life, this is what it would look like. You would end up with this solid gathering on the bottom of your beaker. All right, some words that you need to know, some vocab. Soluble means it's a solid that dissolves in, or soluble is a solid that dissolves in solution. It's aqueous. That's like if I put sodium chloride in water, it is soluble. It breaks up into sodium ions and chloride ions. Insoluble things stay as solids when we put them in water. So like silver chloride. If silver chloride goes into water, nothing happens. It doesn't break up into its ions. It stays as silver chloride, the solid. So insoluble things are not aqueous. They stay as solids. They stay together. And sometimes you see slightly soluble instead of insoluble, but we can use those interchangeably. All right, you have these on your paper, simple rules for solubility. The really important ones are anything with a nitrate, so potassium nitrate, silver nitrate, ammonium nitrate, all of those are soluble. So anything with a nitrate is soluble. Anything with ammonium, your alkalis, your group 1, those are all soluble. And then you can kind of use these as a reference guide. So you can figure out what the solid or the precipitate would be during these precipitation reactions. When we're talking about precipitation reactions, we want to use different types of equations to describe them. What you're used to is the formula equation, or it's sometimes called the molecular equation. we write things completely out and we leave them intact. So even though they're aqueous, we write it together. An example here is using silver nitrate and sodium chloride. We know silver nitrate and sodium chloride are both aqueous, and if we put them together, we're going to form silver chloride, the solid, and then we'd still have sodium nitrate, which would be aqueous. We've written all the reactants and all the products as compounds. We haven't broken anything apart. Then you can take it a step further and you do the complete ionic equation. The complete ionic equation, you take strong electrolytes and you break them apart into their ions. So our strong electrolytes from the example that we used up here are your things that have the aqueous subscript back here. So all of those get split up. So silver nitrate really is silver ions and nitrate ions. Sodium chloride is really sodium ions and chloride ions. And then silver chloride is a solid. It stays together. Do not touch it. Leave it as it is. So your solids stay intact. And then we have our last one, which is the sodium nitrate, and that will also split into sodium ions and nitrate anions. So your formula equation, everything is a compound, your complete ionic, you split up all your aqueous things. All right, your net ionic equation is where we show only the ions that go to form the precipitate. So if we go back really quick to look at our net ionic, what we would see is that sodium stays as an ion on both sides of the reactions. So I ignore it. It's called a spectator ion. The same is true with our nitrate. It's here and it's here. It just stays in solution floating around as an ion. It doesn't change. What we focus on when we do the net ionic are the two ions that come together to form the precipitate. So if we go back to here, you can see that the net ionic would be the silver ions and the chloride ions producing the silver chloride solid. And we could say that the sodium ions and nitrate ions are the spectators. They don't change, they stay as ions on both sides. So we're going to do a couple examples with this. We're going to write out the formula equation, the complete ionic, and the net ionic. So here we go. All right, potassium chloride. Potassium chloride, and they tell me it's aqueous, reacts with aqueous silver nitrate. Silver is a +1, nitrate's a -1. And we have to predict products. So the potassium will go with the nitrate, the silver will go with the chloride. And we know from our previous example that the silver chloride will be the solid and the potassium nitrate will be aqueous. If you end up with two products that are aqueous, that means you have no reaction, because what you're going to see is all your ions go into solution and they just stay there. Nothing happened. So if both your products are aqueous, no reaction occurred. You just put no reaction and you move on. But with this one, something did happen. We got silver chloride solid right there. That's the formula equation. Then we need to do the complete ionic. So that'll be number 2 right here. This is the one that takes up a lot of room because I need to take all my aqueous things and I'm going to put charges with them. I'm going to make them ions and I'm going to split them apart. So it looks like this. I got to do the same thing with my silver and then my nitrate. I leave my silver chloride intact. Don't touch it. It's a solid. And then the last one is the potassium and the nitrate. I may squeeze it in. There we go. That would be the complete ionic equation. Then to do the net ionic, we'll call that number 3 down here, we have to get rid of spectator ions. I can see that there's potassium ions on both sides that haven't changed, and there's also nitrate ions on both sides that haven't changed. So what I'm going to end up with then is my silver ions reacting with my chloride ions, and you can put those in any order. I could have put the chloride ions first and then the silver ions to give me silver chloride solid. That would be the net ionic equation. I got rid of the spectators. All right, the next one here is asking us if aqueous ammonium carbonate. So ammonium is a +1, carbonate is a -2. So I need 2 ammoniums for every 1 carbonate, and it's aqueous, is added to aqueous lead 2 nitrate. Remember that 2 means that lead's a +2 and we know nitrate's a -1. So it'd be PbNO3 and I need 2 of them. All right, now we're going to think about what do we form here? Ammonium nitrate and lead carbonate. If you see lead, it's a good bet, unless it's a nitrate, that lead is going to precipitate out. It's going to be insoluble. And we know both ammonium and nitrate are soluble in water. So we know that is going to be, we'll just go ahead and put that first. The ammonium nitrate is going to be aqueous. It's soluble. But the lead carbonate is our solid. And then to balance it, I have 2 nitrates, 2 ammoniums, so I need to put a 2 right here. All right, that is the formula equation. To do the net ionic, not the net ionic, the complete ionic, take everybody that's aqueous and split them up, making sure that we pay attention to subscripts. So that breaks up into 2 ammonium ions, not just 1, there's 2, and 1 carbonate, and a lead with a 2+ charge, and 2 nitrates to produce, we're going to come down here, 2 ammoniums, and that 2 is going to go for both of those. So 2 nitrates, and then we don't touch our solid, we leave it together, so lead 2 carbonate stays intact like that. So that would be our complete ionic equation. The net ionic, we want to cancel out the spectator ions. So ammoniums on both sides go away, nitrates on both sides go away. I'm left with the carbonate ion and the lead ion. Those 2 things are going to come together and they're going to produce the solid lead carbonate. So there would be your net ionic. Okay, the last thing we need to talk about in this podcast is solution stoichiometry. We want to be able to predict all sorts of things based on 2 solutions being mixed together. So here's some key steps, things that you need to be able to do in order to do solution stoichiometry. You need to make sure you can identify the species present in the combined solution. That means you need to understand what the precipitate is. So you need to know your solubility rules. You need to be able to write those formula equations, write the net ionic equations, and all of that depends on you being able to predict what the precipitate is. And then the rest of it is calculating moles of reactants, limiting reactant, moles of products, grams, other units. This is kind of your regular basic stoichiometry, nothing really new with that. We have 2 problems to do with these. So for the first problem, it says, calculate the mass of solid sodium chloride that must be added to 1.5 liters of 0.1 molar silver nitrate solution to precipitate all the silver ions in the form of silver chloride. So we have this solution, and we know if it's silver nitrate, we really have silver ions and nitrate ions. We want to know if I add sodium chloride, how much of that do I need to add in order to get all the silver to come out of solution in the form of silver chloride. So the first thing I'm going to do is really quickly, I'm going to write my formula equation. I have silver nitrate and sodium chloride, and that's going to produce silver chloride and sodium nitrate. That's balanced, and then I want to do a quick net ionic. So I'm going to skip the complete ionic step. I am just going to write the 2 ions that go together. So my silver ion and my chloride ion are what are going to join together to give me my silver chloride solid. And if we think about this, that obviously comes from the silver nitrate. and this comes from the sodium chloride. So to do this, I am going to first figure out how many moles of sodium ions, not sodium ions, how many moles of silver ions I have here that I'm dealing with. So I have to use the molarity equation. 0.1 molar equals how many moles of silver nitrate in 1.5 liters. If I do that math, I come up with 0.15 moles of silver nitrate, and because I care only about the silver ions, I know that that's also equal to the moles of silver ions because there is one silver in one of these, so their molarities are the same. Okay, that is going to be my starting point for my stoichiometry. And I know that for every 1 mole of silver ions that I have, I need 1 mole of the chloride ions to react with it. And that's from my net ionic equation. And then I have to look at my chloride ions. They're coming from sodium chloride. That's how I'm putting it in. So if I need 1 mole of chloride ions, I need to add 1 mole of sodium chloride because there's 1 chlorine in the sodium chloride. And then they didn't ask for moles, they asked for mass. So I have to do that last step where I say 1 mole of NaCl is 58.45 grams, just the molar mass off the periodic table. So those go away, those go away, those go away. And if I do all that math, I am left with 8.77 grams of sodium chloride. So this is pretty basic stoichiometry. This isn't anything new that we haven't done before. The part that's new is using the molarity equation and breaking down into concentrations of ions. So just a little bit of some new stuff. Okay, last question here. When aqueous solutions of sodium sulfate and lead-2 nitrate are mixed, lead-2 sulfate precipitates. Calculate the mass of lead-2 sulfate formed when all of that blah 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 blah. This is going to be a limiting reactant problem because they're telling me I have this much of one reactant, I have this much of the other reactant, how much can I form? So the first thing we want to do is let's write our formula equation here. So I have my sodium sulfate reacting with my lead-2 nitrate. And they told me that the precipitate or the solid is the lead-2 sulfate, which means that the sodium nitrate is my other aqueous product. And that's going to need a 2 to go with it. So here's this. Let's write our net ionic. So I care what goes into the solid right there. So I'm going to have my lead ion reacting with my sulfate anion, and that's going to produce the solid that I'm looking for. Okay, so that being said, I'm going to have to figure out how many moles of lead are in this, and how many moles of sulfate are in this. So I'm going to have to do 2 quick little calculations first. I'm going to use the molarity formula. Some number over 1.25 liters. And I'm going to do the same thing with the other one. So I have 0.025 molar equals X over 2 liters. So if I do the math on the top one, I'm going to come out with 0.0625 moles of the lead-2 nitrate. And the one on the bottom, we're going to come out with 0.050 moles of the sodium sulfate. Okay, the part I want is that and that. So if I look at the ratio, there are one of these in one of the molecules there. So that means that the lead ions are going to have the same concentration that we just, or the same number of moles that we just figured out. And this is true here. There's one sulfate, so the number of moles of the sulfate anion are going to be the same as the number that we just figured out. Now, because this is a 1-to-1, if I divide both of those by their coefficients, that tells me that the smallest one, which is the sulfate, is going to be the limiting reactant because I have the least amount of that I'm going to run out of it. So this is the one I'm going to run my stoichiometry formula with. So I start with my limiting reactant. Oh my goodness. Oh boy, not getting any better. All right, I need to go to grams. I think that's what it's asking me. Yes, mass of lead 2 sulfate, grams of this. So for every 1 mole of the sulfate ions that go in, and that's from here, I produce 1 mole of the lead 2 sulfate solid, and 1 mole of that solid is 303.2 grams. Take all that into your calculator and you end up with 15.16 grams, but significant figures, there's 3. So that's going to equal 15.2 grams of lead 2 sulfate. All right, so that one's kind of the same as the first one, except we had to deal with the idea of a limiting reactant. Okay, that's the end. We're going to do practice with predicting the amount of precipitates that should be formed in class, so make sure that you're comfortable doing that stoichiometry and using the molarity calculations in order to do that. Also make sure that you have a good idea on the solubility rules so that you can predict what the precipitate will be in these precipitation reactions.